Okay, hi. So this is the fifth seminar, and this is part one of a two-part uh, session on binary execution and particularly system startup. So when we compile and build a file, we rarely on host development, when we're just compiling on a normal system, quite often are very aware of the complexities and the things which are necessary in order for a program to run. So for example, here I've got a program called predictably test.c, and it is pretty pointless. It sets a variable and prints hello world and then exits. Now, if I build that program, so I'm going to build it and put the output file into test, and I'm going to call it static, test static, and I'll explain why in a moment. Minus s, oops, if I could type, static, and then test.c. So now what that's actually built is we've got /test static, and it prints out hello world and increments a variable for reasons best known to itself. Now, if I actually build that program, but I don't link it, so this is just going to be, and I don't need to say minus static, because static only refers to linking, and this will become clear in a second. Now if I ask the system, so we've got the two files there, we've got test static and test.o, and the system can distinguish these fairly well. They're both ARM, one of them's statically linked, and one's executable and one's relocatable. Now if we look at, for example, the size of those two files, so if we start with test static, then you find it's fairly big. Okay, that's a fair-sized file. Certainly it would kill our single board computer. However, if we look at test.o, it's pretty tiny actually, and compared with the size of test static, it's tiddly. Now its size is part of binutil, part of the binary utilities, so it's telling us various bits of information here. It's telling us how much code there is, so 98 bytes in that one, and 82,000 there. There's no data, no uninitialized data, whereas this one's got quite a lot. Now if we use another feature of binutils, which is NN, now NN, like most of these things, it's very truncated, stands for names, and it gives you the list of names in the program. And this can be everything from variables to function calls to bits of code and stuff like that. So it's stuff that the system can see. And if we do test.o, there's very little there. It's got main, and it calls, strangely not printf, puts, the put string routine. Although it says it's printf, it actually calls put string. And the U means undefined. It doesn't know where it is. It just knows who it's got to call it, doesn't know where it is at the moment. And that's why it says it's relocatable, okay? Because it still hasn't really been decided. And you'll notice that the T for text says that it executes from 0, 0, from the start of memory, which is plainly not really true. Now if we do the same on test static, and I'm going to pipe it into more because we now see there's a hell of a lot more. And the addresses are starting to look a little bit more realistic, in the sense that they're not clearly in, what would be ROM, system ROM. And lots of functions are bought, all sorts of functions, app fork, mem, backtrace, all sorts of system stuff which it needs to do. And there's quite a lot of it there, okay? The upper and lowercase means global and local. So a lowercase variable is local to those particular functions. And there we are, there's quite a lot of them, okay? And somewhere in there there's main. Okay, just go on. Now, just to show you, so that's just to run that piece of code. It's got a lot more going on in there in order to just execute that bit of main, which does very, very little. Now, if we actually compiled it the way that GCC and Linux wants us to compile it, and we'll just call this the output file test.bin, oops, and it's test.c. Now if I say what's test.bin and test static, you'll see they're very, very similar, except this one, test.bin, is dynamically linked, okay? And it even says who's going to do the linking. So there's going to be a program called LD64 LD-Linux blah blah blah, which is going to load in the extra code to do the dynamic linking. This one's statically linked, and that's why it's got so much in it. Now if we do size on test.bin, we'll find that compared with test static, oops, if I could find it, it's a hell of a lot smaller. It's still nowhere near as small as the original test.o, but it's a hell of a lot smaller than the static. So clearly, dynamically linking is a good idea. However, we can't do it on our Olimex boards because the Olimex boards don't have an operating system, and they certainly couldn't run a dynamic linker. Now, theoretically, well, no, it'd be impossible to imagine implementing it. If you could implement it, there would be no space left to run any actual codes or programs. Now, that gives us some sort of idea of what happens when we build a program on our host system. Now, when we go across to our Olimex files, we're actually in some ways doing something which is much more complicated, and in some ways it's much more simple. And I'll explain what I mean. It's much more simple in that the processor is a simpler processor. It's nowhere near as sophisticated as a Pentium. Okay, it's a low-powered 32-bit microcontroller, really, microprocessor, and it really has none of the sophistication of a Pentium. However, when we run code, we don't have an operating system, so we have to do the startup of the system. We effectively have to boot the system each time we download and execute the code. Now, if you had to do that every time you booted up a desktop or a laptop or even your phone, you would get pretty bored with it fairly quickly. Okay. Now, if we look, so I'll just check to see demo.elf is up to date. We've got a small number of files here, and demo.elf, now obviously I'm going to have to use the r-none size, and we can look at demo.elf, and you know, it's a reasonable size file compared with the stuff on Linux. It's quite tiny. But if we look, say for instance, at main, again, the constituent part is very small. Okay, and main does a lot more than the test .c does. So it's a substantial file. It's even got 4 bytes of uninitialized storage. So it's pretty big, really. And the other files are obviously going to increase that size. But in fact, all of the files that are there are in our directory. Okay, so all of the .o files, if we just have a quick look, are there. So we know exactly what's going into demo.elf. Now, with the Linux one, we were actually getting stuff that was supplied by the system that we basically have. We have some control over it, but not very much. And in general, most people would not even know that this was going on. Now, if we look inside the program, and if we do an objdump -d, so we're going to look at the disassemble demo.elf to see what's going on in there, we'll find that there's this bit of stuff at the beginning, okay, and this needs a fair bit of explanation, and I'll skip on to that a little bit later. But what we actually find is that there's a fair amount of what seems to be system stuff, and then eventually we get to our main code, and it takes a wee while before we get there. In fact, I may just... there it is, main. So it's a fair way on before we get to main. Now, what are all these other functions which are being called? Well, you can see a number of them are initialization routines, system init, system clock update, so on and so forth. And this is clearly some initialization code that we're calling in through our .o files, okay? Through these files. And if we looked in each one, so if I looked in nm system.o, we'd find there's some of them. So system inits come from there, set system clock to 72, that's the speed of the CPU, so on and so forth. In fact, GPIO will be the large one. So if we do STM32 F1X GPIO F1X underscore GPIO dot O. And that has, in fact, I'm not entirely sure that all of those are entirely needed. I'm pretty sure that it doesn't need the Ether media interface config calling, so it's clearly being a little bit inefficient, and we could probably make the program a fair bit smaller, which is really important to us. And in fact, if we didn't use the library at all, we could make the code a hell of a lot smaller, but it would take a lot longer to develop and a lot more understanding of the system. So there are trade-offs when you use these routines. Now, one of the first things we need to know is a little bit about the memory map of the Cortex-M3 processor. And if we just go back to the initial screen, this is the Cortex-M3 memory map, and you can see here it starts at 0, and 0 is very important to the system, because 0 is where it will be able to look. In fact, the two addresses that are very important tend to be top and bottom, because they're really easy to get to. You don't need to do much addressing there. Now, that is code, because it's going to execute it, and a very important bit of that memory is reflected in to that first 4 kilobytes of memory, and that can either be from user flash, which is 8 and 6 zeros, system memory, which is 1 FFFFFF000, or embedded SRAM, which is the SRAM here. Now, this allows, first 2K of memory is mapped. It's 4K. The first 2K of memory is mapped. Now, this allows us to decide how we're going to boot the system. The default, which is how our machines are set up, because there are a set of pin settings on the board which can change this, is to map user flash into the bottom of memory. System memory is used as a sort of boot, a boot of last resort, so you would flash that with some rescue code. And SRAM is there so that you can actually boot the system as if it were running from flash without writing flash, so it allows you to test the system. So these addresses are quite important, and this is fixed, okay? So this is how the system starts up. And all microprocessors will have some schema like this in order to execute code and in order to start up. So if we now go and look at our code, so here we could see the addresses. These are the relocatable addresses of the various functions. But if we look in the demo.elf, we see that it starts in 80000. Okay, so it's starting in the beginning of user flash. So clearly that's in the right place, that's where we want it to be, and this we will see later on how the compiler knows to use these addresses. And then there's this big mass, and this just means that things are repeated, so it's not really showing us, or it's either that or it's empty. And this is sets of code which the system, it's effectively a table, okay? So that's why that looks like that, and I'll explain that much more later on. This is normal sets of code, default handler, reset handler, and so on and so forth, and system init. Now, we do have this code, so we can look at it and see how the system is set up. So if I now look in startup.c, we can see that, in fact, if I look in using Emacs, much better, because it's got colours, hopefully you can see all this, we've got default handler, okay, and we've got a declaration of reset handler. Now, default handler is actually very boring. And this is just basically saying, if I get called, do nothing. And basically, this is really saying, I'm not defined, I'm undefined, I can't do anything. Now, this is very important and very useful. Reset handler is initialized down here, and we'll notice that reset handler eventually calls main. So this is clearly very important. So reset handler is the starter of the system, essentially. Okay, and basically it's called reset handler because reset is the start signal for the entire system. If you press the reset pin or power up the machine, that's what it does. Now, there's a few other things that we need to understand here. There's some variables that at the moment are going to seem a little mysterious to us, but they'll be explained later on. And also, there are frequent references to things with attributes of weak. Now, there's a couple of things worth noting here. Quite a lot of stuff in these files will have lots of underscores, either one underscore or underscore underscore or underscore underscore ended by underscores. Now, nearly always, this means that they're hidden, and generally they're not seen. It's a bit like dots in the front of files. You don't normally see them in the run of things. And the more underscores you have, I mean, the more hidden they are. So that's why it's trying to just keep these things from visibility, really just not to confuse people. Now, weak is really meaning, this is I'm trying to use the correct word, not suggestion, it's a sort of recommendation to the linker that this is a weak function call, so it can be overwritten. So normally if you have two function calls with the same name, the linker would say, I can't have that. So if you declare printf twice, it would say, no way, you can't do that. I only can have one. Now, if it has weak in front of it, it means that it will select the non-weak one. So what it means is you can override this. And the reason for that is that you may eventually, and we will eventually, have some libc initialization code which will do something, because this one does nothing, okay? It calls it, it does nothing. And it's just really there as a placeholder. And later on we'll see down here in this thing called the vector table that the nearly all of the routines in the vector table, in fact all of them I think at the moment, well not entirely all of them, because there are a couple which aren't weak, but we can't see them at the moment, are weak. So this means that if later on we get a handler for one of the UARTs, which you will do, then it can override this, okay? Now, this table is, and we'll see later on how this happens, is put at the start of memory. So this is put right in the beginning of user flash memory, so that this is at the beginning of where the system starts. So down here, we'll actually see that it actually puts the this section, and it calls it .isr vector, interrupt service routine vector table, okay? And it then, through a bit of GCC magic, points to a huge array of all of these addresses. And the first two addresses, that one there, eStack, we'll find out about a little later on, but it's basically setting up the stack pointer. And this one here is reset handler, okay? Which is just up here, okay? This is this piece of code here. Now, reset handler is clearly very important, and these two first 32-bit words are used by the system because it expects two things when it boots up. It needs a stack and it needs some code. And it needs the stack in order to execute the code, and it needs the code in order to start up the system. So it starts the system with reset handler. And as we've seen, that eventually calls main. But before it calls main, it needs to do some things. And those things are initialization routines, and it's setting up these two areas here. What's called the data area. So, and you'll see that it's got the address here at the start of data, and it starts at the start of data and then goes up to the end of data and just initializes it with whatever values are required. Okay, and I'll explain how it gets these labels later on. So at the moment we just have to accept that they are somehow given to the program. They're externally declared, which means that someone else has told the program what these values are. And then it needs to initialize the uninitialized section, which is called a block store segment. Now, this section, the data section, needs to be initialized with something. So that has to be set to the actual data itself. The uninitialized data just needs to set to 0. Okay, so that has initialized the two segments, the data segment and the uninitialized data segment. The code segment is written from the binary file by the flash write image command. After it's done those two, it calls system init, and system init is a routine which is given to us by STmicro in order to initialize the processor. Okay, and then it calls the dummy routine libc init array, which does nothing, but later on will be necessary, because at the moment we're not really using any C library routines. That's what libc is. Finally, it calls main, goes off and does whatever it has to do, flash LEDs or send characters down the serial port. And if by any chance main terminates, which will depend on what's in the code, but generally it doesn't, if it does happen to terminate, then we just make sure that this code runs forever, because there's nowhere for it to go. Okay, it can't. Now, in the Linux code, it would go back and call the operating system. Okay, so but we don't have an operating system, so all we can do is just loop forever and hope that the person resets the board and reloads something sensible in. So that's what actually happens when you initialize a program. And in the next seminar, I will give you some details on how some of these addresses are actually found. Okay, thank you very much.